Yes, sir.
So I think we will try to summarize all the postulates today. So postulates of quantum mechanics. Okay, so I'm going to summarize many of those things in a way that is you will appreciate what all you have learned. So the first one that I will try to summarize is that the state of a quantum system is a ket denoted by psi, which is an element of a Hilbert space. Second, physical observables are self-adjoint operators acting then we have so we have talked about these two postulates so far, and let us understand what that means. That means for every self-adjoint operator, A we have A acting on some phi n is equal to A n phi n, where this set of operators phi n, a set of states phi n, are eigenstates of A with real eigenvalues given by this set A n, and this phi n forms a complete orthonormal basis for the Hilbert space H. That means you have phi n phi m, the inner product phi n phi m is delta nm. This is the statement of orthonormality, and sum over n, outer product of phi n with phi n, sum over all n is identity. This is completeness of the basis. So The eigenstates of every Hermitian operator will satisfy these two things, and then it will become a complete orthonormal basis for A is any self-adjoint operator. So for every self-adjoint operator, this is correct. Now we can say that if the observable A is measured in an arbitrary on a system in an arbitrary state psi. Okay. Now the result or the outcome of the measurement is randomly one of the eigenvalues of the self-adjoint operator A. So important to understand this word randomly. That means we do not know what is going to be the result. We can only say that what are the possible results. Possible results are the eigenvalues of the self-adjoint operator. Okay. Now one can understand two things. So suppose if you are so let us say that we have a system, okay, and you have, let's say, some kind of a meter. This is what measures A. Now if the system, let's say, is in a state phi L, for example, system is in this state phi L, then the A meter will show the value AL, and this can be predicted. Okay, can be predicted. Okay. And let's call this as prediction. Okay, and we make what kind of a statement we make in this case is that A is sharp in phi L. Okay. Suppose if the state is some arbitrary state psi, okay, then A meter can show, so the result belongs to this set, only that you can say, and cannot be predicted. In which case we say A is dispersed. A is dispersed in set. So sharp and dispersed. This is the language which we use to understand this. Now, what quantum mechanics? So this is a general case. Okay, so this case is a general case. You cannot expect that the state will be always an eigenstate of the operator. So this is the general case. So we ask a question: what happens in general case? So in general, if the state of the system is psi and it is not an eigenstate of A, not an eigenstate of A, then we measure A, okay, we measure A, then the result is dispersed. Okay, we cannot predict the result and the result is dispersed. Now we ask at this point, what does quantum mechanics tell us in this case? Or you don't want to tell us what quantum mechanics give us in this case. What does quantum mechanics give us in this case? Now quantum mechanics gives us the following. So since these phi n form a complete orthonormal basis for the Hilbert space H, psi admits an expansion in this set phi n. So this is the basis. So I could write psi to be equal to sum over n, some complex coefficient Cn. Okay. Now this expansion tells us that, so this is allowed, where this Cn is obtained by taking an inner product of this phi n with psi. Okay, and then probability that A meter shows the result AL is given by, we call this as, let's say, P of AL, that is equal to CL modulus square, which is equal to the projection of psi on phi L modulus square. So what quantum mechanics give us? It gives us probabilities. Okay. So what is it that we have? We have probabilities. So it is a statistical answer that we get. We don't get, whenever A is dispersed, we have only a statistical variation. That means it can be A1 with a probability C1 square mod, if A2 with a probability C2 square mod. So results, if you ask a question, it could be A1 with the probability mod C1 square. It could be A2 with the probability mod C2 square, and so on. And AN with the probability mod CN square, and so on. Okay, so these are possible results, and then respective probabilities. Okay. Now we ask a question that So if I ask the following question, what is the value of the property A in state psi? Suppose if I ask this question, is there an answer to this question, or can we think of providing an answer to this question? Now there is no one value for this property. The property can be, because your A meter is showing sometimes A1, sometimes A2, sometimes AN, etc. But if you want to say that we have to describe some value for this, we look at some of our experience in doing experiments. If you are trying to measure some experimentally, you are measuring some property, and sometimes suppose you are measuring acceleration due to gravity, sometimes you get 9.7, 9.6, 9.9, 10, like that, different values per meters per second square. So what you do is that because the variation in this value of measurement is because of some changes in your experimental conditions, which you don't have perhaps control, otherwise you could have controlled it. And hence what you do is that these random fluctuations in the answer are taken care by taking an average of the results. So here also we do the same thing. So this value is, so what is the value of the property A in state psi? So the quantity that can be defined as an answer to this question is the average or mean value of the result. Average or mean value of the result. That means you're going to write sum over n modulus Cn square. This is the probability into An. So this is what gives you average value of A. Okay. So in quantum mechanics, we call this an expectation value. Expectation value of the operator A. So in postulate 3, quantum mechanics tells you how to calculate expectation value. So given the state psi, normalized or otherwise, so it may be normalized or it may not be normalized. Given the state psi, the expectation value of the operator A in state psi is given by expectation value is always related with the two angular brackets, is equal to psi A acting on psi. That is, you act A on psi and take an inner product with psi, divided by psi. Now this denominator will become 1 if psi is normalized. If it is not normalized, then you divide by the norm of that state. So this is the statement of expectation value. So expectation value is the quantity that measures in some sense what A is in a state that is where A is dispersed, where any operator is dispersed. Okay. Now you can also ask a question: is the expectation value? But you can also say that okay, dispersed. But you can also talk about. So the next question that we can ask is, okay, A is dispersed in psi. Okay. Now we can ask a question: how much is the spread? How much is the spread? How much is the spread? That you can calculate by calculating what is called statistically variance. Okay, so you calculate variance. Okay, so how is variance defined? Variance is defined as so you consider an operator A. Okay, you consider an operator A, and then remove the average value of expectation value of this one. This is a scalar quantity, so you multiply with this identity operator, and then square this one, and take an expectation value of this. Okay, so this provides something called what is called a delta A the square. This is called the variance. So the spread is actually square root of this one, that is delta A. So delta A defines what is called spread of A in psi. Of course, this is the expectation value is taken with psi. Okay, so in psi, which is what we call as uncertainty. Uncertainty. Okay, this is the spread. Uncertainty is basically spread. Okay, now you can actually write this. Okay, so we can show. I will leave it for you to show that. We can show that this delta A the square can be written as the expectation value of A square operator minus expectation value of A the square. Okay, that is starting from this definition. Okay, start from the definition that I have written here, and then you can show that this is equal to this. Okay, so the uncertainty can be calculated by just calculating the expectation value of A square operator and expectation value of A operator, and then use this expression to find out uncertainty. So this is a measure of the extent of dispersion. Okay, so in all likelihood that we can state about the property A in psi by giving the expectation value of A and the uncertainty in A. By giving these two numbers, we will be able to talk about the property A in that state psi. Okay, so this is the third postulate. So third postulate is with respect to finding the expectation values and uncertainties. Okay, now let us look at the fourth postulate. This is quite important. Okay, so fourth postulate is to do with the dynamics. Okay, so that is essentially time evolution. Time evolution of the state now. So what is the statement of the time evolution? The time evolution, the postulate is something like this: given the state at time t equal to 0, that is psi of 0, we solve what is called Schrodinger equation. Schrodinger equation given by IH cross dou psi t by dou t is equal to a Hamiltonian operator acting on psi of. Okay. Now, when we talked about Schrodinger equation earlier, we said kinetic energy plus potential energy, and that is what we call as the Hamiltonian, where H operator is the Hamiltonian operator. Okay. Now we have, so H is usually a function of x and t. Okay. So classically, H is a function of x comma p. Let's say one dimension. So correspondingly, in quantum mechanics, we have H operator is a function of x operator and p operator. X operator and t operator. Okay. Now, in coordinate basis, we have already seen, that is in coordinate basis. So at this point, let me make a small distinction between the choice of the basis. So in coordinate basis, what happens to psi? Psi is interpreted in coordinate basis by taking a component of psi along x, which is what is a wave function. So if we are working with coordinate basis, then these operators are defined like this. That is, x operator acting on psi of x is equal to simply x multiplied by psi of x. And p operator acting on psi of x is equal to minus IH bar into d by dx acting on psi of x. Okay, so this is what happens in coordinate basis, what these operators are. Now I could have also chosen a momentum basis. Okay, so in momentum basis, so that means what? I'm having this phi, I will now project it onto along the direction of psi t. Then this is what you will call it as some psi. So let me call this as some phi. So phi p. Okay. Then the operators are something like this. When x operator is acting on phi p, that will be equal to IH cross d by dp acting on phi of p, and p operator acting on phi of p is equal to p multiplied with phi of t. So now you realize this Hamiltonian operator by choosing one of these bases for further calculations. You choose either coordinate basis or momentum basis, and then this equation can be written as a partial differential equation in time and space or time and momentum. Okay, so depending on, so based on the choice of the basis, the Schrodinger equation can be written as a partial differential equation in T x or T p for further solution. So you have to solve that partial differential equation after recasting that in terms of. So you choose either coordinate basis or momentum basis, then you know how to represent this operators, and then you put in those operators, then it will become a partial differential equation, and you solve that partial differential equation for a given boundary conditions. But before we do that, and this is what we are going to do in the rest of the course. In the rest of the course, we are going to solve these partial differential equations. That's all that we are going to do. And in fact, we will do something much more simpler than this. We don't even solve the partial differential equation in Tx. Sometimes we solve only in x or in x, y, z for that matter. Okay. So let us try to remain with this equation for some time. That is, let's try to do something formally. So that is, let us solve Schrodinger equation formally to understand some interesting structure. Let's solve Schrodinger equation formally. Now, what do you mean by that? That means I have this IH cross dou psi of t by dou t is equal to h psi of t. Okay, so here I would like to assume, assuming that h, the Hamiltonian, is independent of time. Okay, if Hamiltonian depends on time, we have to worry about it differently, but let's assume for the time being that h is independent of time. That means energy is conserved. So it is like this. Now this I can write it formally in the following fashion. That means I am not worried whether h is an operator. H is an operator, but I am not interested in asking what is that operator and so on. So this is a first order differential equation in time, right? So I can solve this. Okay, formally solving this, we get something like this. Psi of t is equal to e to the power minus I by h cross into t operator h acting on psi at 0. Okay, so this is a formal solution. Okay, so from here to here we come, this is a formal solution. That means it is just a formula. We cannot, of course, we have to ask what is the action of this operator on this. Okay. Now note two things here. The first thing is that since Hamiltonian operator is Hermitian, Hamiltonian operation is Hermitian. Now this operator u of t, which is equal to e to the power minus I by h bar e h, this operator is unitary operator. What is unitary operator? Unitary operator, you can show that u of t into u of t dagger is equal to u of t dagger and u of t, that is equal to identity. That means u of t is, so basically what is u of t dagger? If u of t is this, then u of t dagger is going to be equal to e to the I by h cross e into h operator. So when you multiply these two things, it will become identity. E power 0, that is identity. So this is unitary. Okay. So notice that you start with psi of 0 and then act on that a unitary operator which is given by this, then you get psi of t. Okay. This means, this implies that evolution of a quantum state is unitary. Unitary evolution. What does that mean? That means, suppose you have this situation, then you ask what is psi of t a bra vector. Okay, so note that if psi of t is this, then a bra psi of t is actually a bra psi of 0 and u dagger of t. Now suppose if I ask what is the inner product of psi of t with itself, inner product of psi of t, then this is equal to psi of 0, inner product of u, this is psi of t, and u of t psi of 0, this is psi of t ket. So but u dagger u is identity, so this is same as psi 0 psi 0. So what is the significance of this unitary evolution? So evolution, that is unitary evolution of the state preserves the norm. That means if psi of 0 is normalized, so will be psi of t for all t. So that means the normalization will not be changed. If it is normalized at the initial state, the time evolution will not make it unnormalized. So this is what is called unitary evolution. Okay, so this is the first point that we are making after we get the formal solution. Okay, so this is the first point. Okay, so this is what we can call as the first point. Now the second point is something like this. So we have something called psi of t is equal to e to the minus I by h cross t operator acting on psi of 0. Now what does this mean? This means we know that exponentiation of matrix, etc., that we have studied earlier. So this is like, we can write this as an identity matrix or identity operator minus I, or I can say plus minus IT by H bar into operator H plus minus IT by H bar the square into 1 by 2 factorial into H square and so on. Okay, so there is an infinite expansion in terms of the operators, and all of this must act on this psi of 0. So that will be your psi of t. So this operator can be realized in this fashion. Now we can ask a question. Suppose we can have two cases. So let us say case A. Okay, I first talk about case A. Case A is such that case A is the case where this psi of 0 is an eigenstate of this Hamiltonian. Okay, psi of 0 is equal to let's say E psi of 0. That means in this case, initial state psi of 0 is an eigenstate of the Hamiltonian H. Now notice that if this is so, what will be H square? H square operating on psi of 0. H square operating on psi of 0 is H operating on psi of 0, which is equal to E square operating on psi of 0. I mean E square times psi of 0. In the same way, you can say that any H to the power n acting on psi of 0 is equal to E to the n into psi of 0. So in that case, what will happen? So you can see that here in this term H is acting, in this term H square is acting, and so on. So we can see that your psi of t is equal to, let me write down this expansion in this form, that is, now j is equal to 0 to infinity minus it by h cross raised to the power j into 1 by j factorial into h j operator acting on psi of 0. Okay, so this is, I am actually writing this in terms of a summation. But then since hj acting on psi of 0 is e to the j, e power j into hj, so this means we have that is equal to sum over j is equal to 0 to infinity minus it by h cross to the power j 1 by factorial j into e to the power j, this one into psi 0.
Sir, on writing the power series solution of the exponential operator here, it's just the power series form. This minus it by h.
Correct.
Okay.
So that is, so what we can write this one? This is nothing but, I will simply write this again in the exponential form, that is e power minus I by h cross into e into t. Now e is just a parameter, so e into t into psi f. Okay, so now the situation is that the time evolution of an eigenstate of Hamiltonian is very trivial. It is just a complex number multiplied to that. Okay, so this is just a phase. This is just a phase. So time evolution is essentially accumulation of some phase for if the state is an eigenstate of Hamiltonian. Okay, so now let me say that eigenstates of the Hamiltonian are called stationary states. Stationary states. Recall, this word was first introduced by Niels Bohr when he talked about Bohr's orbits. They are called stationary states. So eigenstates of Hamiltonian are called stationary states. Now the time evolution for stationary states is trivial. Okay, so for a stationary states, the time evolution is that it is just multiplied by a phase factor like this. Okay, so for h psi 0 is equal to E psi 0, that means psi of 0 is a stationary state. We have psi of t is equal to e to the minus I by h cross E t multiplied by psi of 0. Okay, so this is something which is a very trivial kind of a time dependence. Okay, but we are again just like in the original case when we talked about measurement. If A is sharp, then answer can be predicted. Like that, if in the initial state if H is sharp, then the time evolution is somewhat trivial. But most general case is that probably H is not sharp. Okay, so that is what will take us to this case B. So case B, that psi of 0 is a non-stationary state. Non-stationary state. That means it is not an eigenstate of the Hamiltonian operator. It's not an eigenstate of the Hamiltonian. Then how do we get psi of? This is the question. This is an interesting question, because if we can answer this question, then our quantum mechanics is done, because most of the states are non-stationary states. Okay, now we can use this formal solution to get an answer for this. Okay, that is the power of kind of a structure of mathematical structure of quantum mechanics. Now, since Hamiltonian is a self-adjoint operator, okay, eigenstates of the Hamiltonian, okay, call, so maybe I will call them as phi n, form complete orthonormal basis of the Hilbert space H. Please remember that this H is for the Hilbert space. I am writing this curly H, and this H is for the Hamiltonian. So let's not confuse these two. It will form a complete orthonormal basis. That means what? That means, so let us say that H acting on this phi n is equal to some En phi n. So what does that mean? these phi n are stationary states. They are eigenstates of stationary states. Now, such stationary states exist because this is a self-adjoint operator, and it also forms a complete orthonormal basis for the Hilbert space. Now, of course, if we don't know, then we have to find them out. Okay. Suppose if we know them. Okay. So if we can find or solve for these phi n's, that means if we can find the stationary states, then we have the following thing. Then this psi of 0, that is the initial state, can be expressed as a linear combination of these phi n's, stationary states, because that will form a basis. Stationary states. Okay, that means your psi of 0 now can be written as sum over some Cn into phi n, sum over n, Cn phi n. Okay, so now we have from the formal solution psi of t is equal to e to the power minus I by h cross t h operator acting on psi of 0. Correct. So this can be now I write it as e to the power minus I by h cross t h. Now this is nothing but sum over n Cn phi n. Now since this is a linear operator, okay, since this is a linear operator, we can write this as sum over n Cn e to the minus I by h cross t h operator on phi n. Okay, since e to the minus I by h cross t h is linear operator. Okay, now what is this one? So this is basically like our case A, because each phi n is a stationary state, and hence we can write this as sum over n Cn e to the minus I by h cross into En into t phi n. Okay, so in this case, use result of case A. So this is done. So we have now found out what is psi of t. Psi of t is basically time evolved linear combination. So linear combination of time evolved states of the stationary states. So the most important thing here is that if we know stationary states, namely eigenstates of Hamiltonian, then we can get the time evolution of any state. This is the power of knowing the stationary states. Okay, if you know stationary states, then that will describe time evolution of any state. Okay, and that is the reason why the central, that is the reason why that implies the central task of quantum mechanics is to get stationary states. Stationary states, namely to solve this problem. H phi n is equal to E n phi n. Okay, and some textbooks or sometimes people call this as, so this is sometimes called as time independent Schrodinger equation. Okay, so some people call this time independent Schrodinger equation. Essentially, this is an eigenvalue problem. Okay? This is essentially an eigenvalue problem. Okay, so this is what we call as the fourth postulate, or namely the time evolution. I want to bring your attention to 2 points. That Schrodinger equation is just a postulate. Like I said earlier, that I am not deriving this Schrodinger equation. And if Schrodinger equation can be derived, it cannot be a postulate. So Schrodinger equation is a postulate. Now I am trying to show you some kind of a structure by solving this formally. Okay, and Adira, you have a question? Adira? Yes, Pranav?
Sir, suppose if I have a random variable xi and a probability distribution f of xi, then the expectation value is sigma xi into f of xi. But if I want to calculate the expectation value of xi square, why is that sigma xi square into f of xi and not sigma xi into xi square into f of xi square?
See, the probability distribution is same for all random variables. Okay, so let us try to let us say your f of x is the probability. This is the probability distribution function. Now xi is a random variable, or x is a random variable, let us say. Okay, continuous distribution, let us talk about. X is a random variable. Then the average value of x is given by integral x into f of x dx. This will be your summation in the discrete case. Now suppose you want x square, this is a different random variable. This is not same as that. So x square, you can call this as some y. So this is a different random variable. It's an independent random variable than x. So you want to calculate x square, you have to consider that as another random variable f of x into dx. You can also take some arbitrary function g of x. This is also a random variable. Okay, so we want to calculate average value of g of x, then that also is equal to integral g of x into f of x dx. So f of x is a random probability distribution for all random variables. Now, depending on what is the random variable, its average can be taken by simply putting that variable there. Okay, so this is basically, this is a continuous version. You want to call it as a discrete version. This will become
my doubt is actually, if I change the random variable, why is the probability distribution not changing? Should it not be f of x square or f of g of x or something like that?
So what I'm saying is that you can take any random variable. So essentially what I'm trying to say is that, suppose let's say that you have x and then some probability distribution like this, f of x. So this is like a weight, right? So probability is like a weight. Now whatever is the random variable, suppose at this point x, you have some random variable that may be x, or that may be x square, that may be f of g of x, whatever it is, it has to be multiplied with the same weight. We cannot keep changing the weight function, right? Weight function is supposed to be a universal function for the whole statistical process, not what you are measuring. In other words, if you are doing an experiment in laboratory, your statistical fluctuations are coming because of the environment. Now, if you are measuring acceleration due to gravity, or you are measuring temperature, or you are measuring something else, the statistical fluctuations will be, your random values will be different. But the statistical fluctuations will always be described by one particular probability distribution function. Correct? So the weights are offered by the environment, and the environment is same for all experiments that you are doing.
Okay, sir, I got it.
So slightly scroll up, sir, in the PDF, I mean the written part. Scroll up, sir.
Yeah.
In the case B. Yeah, up down. A little bit scroll down, sir. Okay. Just a linear combination. Oh, okay. Sorry, sir. Here I got confused. Here the thing is that you are writing that psi of t as this unitary operator acting on the ground state, I mean the stationary state, and then just because it is a linear operator, you are taking that unitary evolution operator inside the summation, isn't it, sir?
Correct.
If it is not a linear operator, I mean if it is not a unitary operator, we cannot take it inside.
No, it's not because it is unitary, it is linear. Linear means I can write. Yeah, linear
so
operator.
Linearly means it can act on any state which has got the summation property. So that is what basically it does. It acts on every term in that summation. That's what you're meant.
Correct. So okay, I can pull out that constant and push the operator inside.
Yes. Okay, sir.
Hello, sir.
Excuse me, sir.
Yeah.
Sir, here stationary state means stationary in time or in space also, sir?
No, it is stationary means, so the name stationary comes because once you give, so probabilities, so let me define this. Stationary state, the definition of stationary state is it is an eigenstate of Hamiltonian, energy is constant, or it is a state in which H is sharp. Okay, so that is stationary state. Stationary state in which the Hamiltonian is sharp. That means That means energy result is predictable. That's what it means. So that is a fixed value of energy is there. So this is stationary states. Now, if psi is a stationary state, let's say psi is a stationary state. Stationary state. Let's say psi 0 is a stationary state. Then you know that psi of t is equal to e to the power minus I by h cross t e into psi of 0. This is how this time evolution will be there. Now you ask what is the probability corresponding to this at time t, that is given by your psi of t, which is same as psi of 0 and psi of 0, because the probability is independent of time. Or if you take, which is same as probability at time t equal to 0. Okay. Or let's say you have for some operator A, you calculate expectation value of A at time t. Expectation value of A at some time t is psi of t A psi of t, which also will be same as psi of 0 A and psi of 0, which is same as expectation value of A at time t equal to 0. So stationary states are the ones for which the probabilities and expectation values are independent of time. Okay, so that is how the name comes. It's stationary in time. So the quantities that we can calculate are probabilities and expectation values, and they are same in time. So such states are called stationary states.
So it is not related with the movement of the particles, sir?
No, actually we have to come out of this movement of particle business, because we don't know, we cannot talk about trajectories anymore. Okay, we can only talk about probabilities, and probabilities are not changing with time.
Sir, probability density also stationary state in this condition?
It doesn't change with time. Yes, it's a function of x. If you are talking in terms of a coordinate basis, then you can call this as a function of x, and that function will not change with time.
Yes. Thank you, sir.
Hello, sir.
Yeah.
Sir, I have a basic doubt. Sir, what's the difference between an eigen function and an eigenstate?
Okay, this is just a terminology. We use eigenfunction and eigenstate in the same sense. Now, the difference is that when we are talking about a ket vector, we always use the word state. Okay, we always use the word state. When you are trying to represent this in the coordinate basis, then every ket vector will be now a function, because we will take the coordinate basis wave function. Then we will call it an eigenfunction. Okay, so essentially, to answer your question, there is no difference. You can interchangeably use both of them. Okay, you can call eigenstate same thing as you can call it as an eigenfunction. Okay, for example, ket is not a function, and hence we will call it an eigenstate. And a wave function can also be called a function as well as a state, and hence in that case we use both interchangeably.
Okay, sir. Thank you, sir.
Hello, sir.
Excuse me, sir.
Yeah.
Sir, when the operator acts on a state, there will be a spread, and we use it as a variance or uncertainty. Then what will be the standard deviation then?
Standard deviation is the square root of variance. So you calculate delta A square and take the square root of that one. That will be your standard deviation in statistics, and that is what we call as uncertainty. The uncertainty in quantum mechanics is essentially standard deviation, what you do in statistics.
So the square of uncertainty gives variance.
Correct. Yes.
Okay, sir. Thank you, sir.
Excuse me, sir.
Yeah.
So like when we define momentum basis, like when position operator acting on phi p, we wrote IH that X position operator acting on phi p is equal to IH cross dy dp into phi of dy dp of phi p. So here how we are getting this relation, I couldn't understand, sir.
See, this relation is, as I told you last time, did you understand how we get this relation when P acting on phi of x is minus IH bar dou by dou x?
Yes, sir.
How did you understand that?
Like, sir, you are asking me how I get the idea of when momentum acting on a phi x?
Yes.
So that's how I took it, because the mathematical that operator is a more physical operator, and what it's act on a wave function is giving me that result.
Yeah, but how is it more physical? So essentially what I'm trying to say is that this is same as that. Okay, but only thing is we are more familiar with the first one and less familiar with the second one. Whatever clarity or lack of clarity that you have on the coordinate basis, same clarity or lack of clarity is applicable for this also. Okay, now this identification of these operators to the differential operators is in some sense it is like we have to identify first some mathematical operations to start with, right? So these are such correspondence that we have identified. Now you are finding comfortable with this association of P operating on phi of x because we have already discussed some heuristic discussion when we did Schrodinger equation. At that time I have chosen coordinate basis representation, coordinate basis I have chosen, and hence it is. If I do the same thing by choosing momentum basis instead of coordinate basis, you would have found this also equally comfortable. Okay, so what I would suggest is you go back to the discussion on Schrodinger equation and now see in what way my choice of Schrodinger, my choice of coordinate basis helped you to understand this. And now you redo that one by choosing a momentum basis. Then you will feel this is also something similar.
Okay, sir. And sir, I have another question, sir.
Yeah.
Like when we say that wave function is equal to summation of Cn and eigenfunction phi n, so is it we are talking about the linear superposition principle, or is it something else?
That's all, because these eigenfunctions of Hamiltonian will form a basis, and any state can be expanded in the basis. So that's all I'm doing.
Okay, sir. And last question, sir.
Yeah.
So like when we this is a more general question, and when we talk about the expectation value, is it not so that when we are trying to find the expectation value of our particular operator, we are basically losing the beauty of this quantum mechanics, because we are more generalizing, and we are not it find more contradicting because what we studied last, that is indeterministic nature. So when I am trying to find this expectation value, whether I am also contradicting the indeterministic nature, or is there any way between where I can take the expectation value as a result of some physical experiment, and with that I can also satisfy the indeterministic nature of the quantum mechanics?
Yeah. So I tried to follow your long question, but I'm not sure if I have followed it correctly. But I think what you're asking is that by settling to define the property A in psi as the expectation value together with a statement of uncertainty, does it tell complete story about that property A in the psi? Is that your question?
Yes, sir.
Yeah.
And moreover, I want to ask that whether this expectation value current contradict the idea of this indeterministic nature of the quantum mechanics.
Okay, that does not contradict, because see what you are saying is that you are not saying A has a specific value in psi. That means your A meter will never show the expectation value as a reading. Okay, so if you have some A meter will show readings on its readout only eigenvalues. The expectation value is never a reading in the A meter. So that tells you that there is an indeterminacy. You don't know what is going to be the reading on A meter. You only know that it is going to be one of the eigenvalues. Quantum mechanics gives you probabilities of the occurrence of different eigenvalues. Now you have to ask a question that, okay, I have to talk about this property A for all states. Now, what is the way that I talk about? This is one way, but this is not definitely going to be seen in an experiment. Okay, so how do you understand this? You can assign this as the property A to this particular thing, and you can always say that this is kind of an average result. This A will tell, this average value will tell you that, okay, this is how the peak, many times this will occur, and with this spread, if you give these two things, you get a sense of what this property is in this state. But this is not going to hide or remove the indeterminacy in any way. It is our desire to have some value for the property A in every state, and this is defined for that purpose.
Okay, sir, but I don't know, but I think I have a wrong feeling of like averaging certain quantity, because when we average, like what I feel that we are losing the individual nature of a system, like individual nature of the particles which constitute a system. And I feel that when we talk of the quantum mechanics, that individual natures of a system is more flourished. I don't know whether I am correct or not, but when we talk of expectation value, I feel that individual nature of that elemental part is lost. And then we are talking about more in general cases, which goes beyond, like, which goes not satisfy idea of the quantum mechanics. That I may be wrong in this.
No, I think what you are saying is correct. Statistically, when you have some random number, that means if your results are randomly varying, now the randomness in the variation can be actually will actually have its okay, let me put it this way. The randomness will be contained in not only the mean value or variance. There are many higher order moments. These are called moments of the probability distribution. Okay, first moment is called mean value, second moment is x square average, third moment is x cube average. So the randomness actually is, you can capture this randomness only when you have all the infinite moments calculated, because all the infinite moments, when you know, that means you know the probability distribution. In that, you are taking only first moment and second moment, that means you are losing significant amount of information. But nevertheless, if the randomness is not so violently varying, or randomness is not so bad, then you will capture a large amount of information by just defining expectation value and uncertainty. So that is what we are settling to in this particular case. But definitely your discomfort is well founded, that there is some kind of a loss, or we are not faithfully representing the indeterminate nature by just considering these two parameters. Well, that is well founded discomfort, and this is what we are doing in this course. And there may be some situations where these two are inadequate and you have to do much better.
Okay. Sir, I asked this question because, like, in my BSc, I found this, like, we did a problem finding expectation value of momentum operator, and then the whole result basically reduced to the classical result. So yes, that's what confused me, and this confusion is still with me.
Yeah, that's right. That's right. In fact, there is a theorem called the Unpressed Theorem, which says that expectation values behave like classical, and they satisfy classical equations of motion. We will prove that here.
Yes. Okay, sir. I understood the idea. Thank you, sir.
Sir, one question
Sir.
coming to my mind from this
Uh,
is average value is equal to expectation value always?
yes, yes. Average value and expectation value are just two names of the same thing.
Yes, sir. And we have seen that time independence Schrodinger equation is an eigenvalue problem.
Correct.
And is the time dependence Schrodinger equation is also an eigenvalue problem?
No, that's not an eigenvalue problem. That is just a partial differential equation. Now, if you solve time independent, that is eigenvalue problem, now these eigenstates of Hamiltonian can be used in the formal solution of the Schrodinger equation to obtain the time dependence of the arbitrary state. That is why finding eigenstates of Hamiltonian are very important.
Yes, sir. And sir, what is the relation of Bell's inequality in this probability? Here we have seen.
Bell's inequality. Bell's inequality is a different story. I think we have to talk about it in a different context. But since you asked this question, let me simply say that Bell's inequality is related to a situation where you have two systems, and these two systems have correlations, mainly by some kind of entangled state. Now, if you do something on this system gets affected. Okay, so now this correlations is responsible for that effect. Now you ask a question, if I make a measurement on this system, we know, so what is the probability of getting a particular value? Now this probability will alter the probability of getting that value. Now this change in probability cannot be arbitrarily altered if you assume that there is a if you assume that what you do here is not going to affect the system here, then there is an upper limit on the value of the correlation that they can have, and that is given by the Bell's inequalities.
Sir, please tell us more about this in another class.
Yeah. So maybe we can either I can tell, or maybe I can I can probably give you one of my lecture which I am currently teaching for your seniors. Maybe I will send you the video. You can take a look at that.
Sir?
Yeah.
Sir, I think he said that some information is lost when we take just expectation A and A square, but I don't think so, sir, because see, when we're taking the probability itself, we're taking the limit n tending to infinity, so there we are not losing any information, no, sir. I'm not getting this question properly, because this makes me think that whatever we're doing is just some approximation. Is it, sir?
See, the question is something like this. So suppose I have a function, this is f of x, this is a probability distribution function. Okay. Now let us try to take a Fourier transform of this function. So e to the f of x into e to the power I kx dx with 1 by root 2 pi integral minus infinity to plus infinity. This is called some phi of k. Okay. This is called a characteristic function. Characteristic function. Now, this is nothing but this is 1 by root 2 pi integral minus infinity to plus infinity. I will write this as f of x into 1 plus I kx plus I kx the whole square by factorial 2 and so on dx. So you can see that this is nothing but 1 by root 2 pi into, you have 1 plus ik times average value of x plus ik the whole square by factorial 2 times average value of x square plus etc. ik to the n by factorial n times average value of x to the n and so on. That means if you know average value of x square, average value of x cube, etc., all the averages, then you can substitute them here. Then we know what is called phi of k. And then you can do inverse Fourier transform. IFT of phi of k gives f of x. Okay, IFT of phi of k gives f of x. That means knowing completely about the probability distribution function, is possible only if you know all the moments. Okay, so that means knowledge of all the moments, is same as the knowledge of f of x. What I'm telling is not quantum mechanics, this is basic statistics. The knowledge of all the moments is same as knowledge of f of x. Now suppose if I know, let's say I know only x and x square. I do not know other moments. I only know x and x square. Now suppose if I substitute that one here, that means I am neglecting these things. I will get some f of x, but that is not the actual f of x. So the random process is not completely characterized or captured in terms of just knowing x and x square. So we have other things which we are not knowing in this. If you know x and x square, and of course you can talk about variance by taking the difference between x and x square. So this is, so what we are taking in quantum mechanics, the results are random, but we are only taking expectation value and uncertainty of that, delta A and this. This delta A is basically square root of this, or A and delta A square. If you take this, that means it is equivalent to taking first moment and second moment. All other moments we are ignoring. That means we are only settling with a kind of a distribution which is governed by only first and second moments. Other moments we are not considering, and to that extent, statistically we have only an approximate description.
So does that characteristic function arises from the fact that it's Plancher's theorem, such that when we change basis from coordinate to position, we take the Fourier transform?
There's nothing to do with quantum mechanics. All this is basically a statistical. Correct.
Because I have read that there is something called as Plancher's theorem, where if we take Fourier transform from momentum basis, we get the position basis and the vice versa.
Yeah, so that is there in quantum mechanics that we will discuss, but this is nothing to do with that. It's just statistics.
It's called characteristic function, Fourier transform.
This is called characteristic function.
Okay, sir. Thank you, sir.
Okay, so I want to make one particular the last postulate of my list, so that we can complete this. And this last postulate is I have 4 here. 4 is about time evolution. So let me now make a last postulate of this course. Okay. So this talks about the measurement. Now, measurement is something which is very, very controversial issue in quantum mechanics. So let me present what is the textbook view or largely accepted view. And of course, I think people have been debating about it for the last 90 years, and hence we can debate it for the rest of the semester. So let us say that let psi be let's assume we will freeze the time for a moment. Let psi be a state, and let's say we want to measure, we would like to measure A. Okay. And we have the following situation: A on phi n is equal to A n phi. That means phi n's are eigenstates of that. That means we know that this phi n forms a complete orthonormal basis for the Hilbert space. This implies I can write this psi as sum over n Cn phi. So far, I have not made any measurement. This is just a description of the state. Okay. So now let's say we measure A. Now we measure A. Okay. With some A meter. And recall that we will not know, we will not be able to predict the result because A is dispersed. But we can say that the result belongs to the set of An. And we can further say that probability of the result An is equal to modulus Cn square. This much is what we can say. Okay. So this much is what we can say. But when you do the measurement, what happens? Okay. Suppose let's say that now A is measured. The measurement is done. And the meter, that is my A meter, showed a reading, let's say AL. It will be one of the eigenvalues. Let's say it is AL. Okay. Then the question asked is, what is the state after measurement? What is the state after measurement? Okay. So this question has an answer in this postulate. Okay. Now, if the result is AL, then post measurement state post measurement state is phi L. Okay. Now this is something very surprising. How do we know this? Okay, how do we know this? How do we know? Now, if you measure A again, if you measure A again, then you get the result AL again. And this can be predicted. This can be predicted. That means what? As we have discussed earlier, we can predict the result only if A is sharp. So A is not sharp. A is not sharp to start with, but when you measure A, you observe a result AL, then A becomes sharp. Then the wave function from this psi, so that means what? So this implies measurement of A changed the state from psi to phi L when the result is AL. Now this change is something which is very different. That means you have a psi which is equal to, it's a linear combination of many phi n's. Now measure A and get result AL, then the state will change from phi to phi L. Okay. So this is what is known with the different names. This is known with the name called state reduction. Or this is also named with the name called wave function collapse. Wave function collapse. This is also known with the name called quantum jumps. Quantum jump. So there is a wave function will change. Now what is important is that this wave function change, or this change is non-unitary. It's not unitary. So that means your normalization cannot be preserved. Okay, it's non-unitary, and it is also irreversible. That means unitary evolution is reversible. If you go in time t like this, if you reverse the time, you can come back to the same state. Now this change is non-unitary and irreversible. Okay. This is a postulate. It is called collapse postulate or quantum jump postulate. Now this is something what seemed to happen, and as you can see that you can ask a question that what is the mechanism of such a collapse? Okay, so a question that has been debated and discussed for the last 90 years is mechanism of this collapse is something that has been worked out by best of the brains in the last 80 years, and there is no final answer yet. Okay, there are many answers, but there is no complete answer yet. Now, the mechanism of collapse is believed because you are having a quantum system, and then in a measurement, you have some classical apparatus that is involved. Classical apparatus. So one has to do an interesting quantum mechanics of a composite system of quantum system and classical apparatus. So people believed that the classical apparatus is a big system, and hence when it interacts with the quantum system in some fashion, then this wave function will lose its coherence, and then it will become kind of a collapse will take place. That is one way in which people have put in a lot of effort to understand this one. And this is one dominant way, but there are many other. In fact, the literature is full of. This is one postulate which occupied the minds of people for the last 90 years. Okay, so let me just say this much about this postulate, and we will. I'm going to now make a statement that I have completed listing down all the postulates, and I would claim that if you have understood whatever we have discussed in these days, you can say that, okay, you have understood quantum mechanics, because these are rules of the game. Now, once you know the rules of the game, you can start playing the game. Does not mean just by knowing the rules you can play the game effectively, but you are ready to play. Now, how well you play the game, because in any game, the rules are actually finite in number. Suppose you want to play chess, then the rules of the game can be just written down on a piece of paper and then given to you. So you know the rules. But then you play the game, it's not the rules that will help you. That based on this finite number of rules, you can make infinitely many strategies. So it is these strategies that will help you to become a great player or a moderate player or a failed player, right? So in the same way, I would say that by understanding these postulates, we have completed the rules of the game. So now we are ready to play. Now, how well you play the game depends on how many good strategies you can make based on these rules. Okay, somebody is called a good worker in quantum mechanics because he uses the same rules, but he comes up with intelligent strategies. Okay, so that is what we will probably do in the rest of the course, understanding how strategies are made to solve problems by using the same set of rules that we have here. Okay, so that is about the rule set that we have. Yeah, I will stop here, and you have any questions you can take up.
Hello, sir.
Yeah.
Sir, Schrodinger cat experiment is also related to fifth postulates, sir.
Yes, it's also related to postulate. It is basically when you don't open the box, you don't know what is the state. The state will be in the two possibilities are there: cat is dead or alive. When you open the box, you will see only one of the possibilities. Okay, and Schrodinger cat, of course, has a little more detail to that. We will talk about it one day, one of the days, but it is definitely related to this collapse of the state.
Yes, sir. But the experiment is done by classical objects, sir.
Correct. So essentially, see, Schrodinger's cat and these kind of analogies, they have some purpose, and we have to understand the purpose, and we should not make them like it is applicable everywhere. Okay, first we have to understand what is the purpose of this experiment, or the example or the analogy that is given. So that analogy
Yes,
is
sir.
not just to understand collapse; it is something more general.
Yes.
But what happens is colloquially, the analogy becomes. It is taught. Sometimes popular books will present it in a different way. So the original issue for which this Schrodinger cat was brought into literature, that keeps changing as many people write different. I wanted to just give you an interesting example, interesting incident. So I think in Kalpakam there is usually every summer they conduct something called summer training in physics. Okay, this Indira Gandhi Center for Atomic Research. And in one of the years, since I am not available, I stay in Kalpakam, but I work in Pondicherry, so I'm available only in the nights. So these people used to call me to give some lectures in the nights. So our lectures used to start at 9 o'clock, and then they will go till first fellow falls asleep, sometimes up to 1 o'clock, 2 o'clock, like that. So there was one class in which two PhD students who are doing PhD in Kalpakam, they wanted to also sit through the lecture, so they came. And the lecture went on up to 1 o'clock, I think. And then after that, these two boys were walking back. They have to walk about something like 2.5 kilometers to reach their place. I offered them to drop, but they said, we will walk. It is nice walking at this time. And when they were walking, there were some police people patrolling, and then they stopped them. And they asked them, where are you coming from and what are you doing at this night? Then they said, we are attending a lecture and coming. Then these police people were surprised that at this hour, what lecture is happening. Then they asked them to come and sit. Okay, explain what is the content of the lecture. These people were surprised and they didn't know what to do. Okay, how to start, because teaching quantum mechanics, and they also sat through the lectures. Then they were saying, you see, there is some state, and then there's a wave function, there's uncertainty, etc., something they were saying. So then one of the two policemen was actually telling, okay, forget about all this. I think you have attended some quantum mechanics lecture, but now tell me whether the Schrodinger cat is dead or alive. So it was very surprising to know that a police person has read about Schrodinger cat, and then he is interested in knowing the final answer. And one of the PhD student was having a quite curious sense of humor, and he said, sir, that case is not solved yet. Okay, so of course, this language of case not getting solved, police people will understand. And so then both police and these fellows had some good laugh and then walked together for some distance. So these people had narrated this in the next class when we met, that this is what happened. So Schrodinger cat is so popular that even people in some other fields like police and even shop owners probably will talk about Schrodinger cat. So one way it is good that Schrodinger's cat is so famous, and it is also that when so many people talk about it, the context and the correctness also gets affected. So that is why I think one has to be very careful in, at least physicists, when they talk, they have to talk it correct.
Yes, sir, it's very popular, but sir, some philosophers have changed the meaning through some books. And
yeah. So that's what I'm saying, that people See, the point is something like this. When I am teaching you people, I am trying to present what I understand, right? And you cannot find fault with me if my understanding is wrong, because only that is only thing that I am understanding, and I cannot borrow somebody else's understanding and teach you. So you have to always take what I am teaching modulo my understanding. Okay, so it's not that I am understanding everything as the truth is. I'm also having some understanding, and my understanding is what reaching you, and you have to, of course, take it as a kind of modulo my understanding. It's not that I understand completely, and of course it is. If it is bad and it is your fate that you have to depend on my understanding. And in science, it is always good not to depend on anybody's understanding. So you take something and then you verify it for yourself, and then believe it only when you are completely understanding it by your own senses and then understanding. Okay, so we always take information from many people and we synthesize our understanding. That is the best way to learn science.
Yes, sir.
And if I write a book, I will write my understanding, no? Because I cannot, I will say this is what it is. And my understanding has a limitation. That is the upper bound, right? I cannot write anything better than what I understand.
Yes, sir.
Sir, this hidden variable theory comes out from this measurement